good morning. In today's class we will look at the following. We will look at the theory of rocket propulsion again. We derived the rocket equation in the last class. We also looked at staging, we looked at clustering of rockets and also the strap-on rockets and what function they do, but we did not really calculate what is the type of acceleration what we can get from a rocket at takeoff, let us say. See, this will illustrate to us in a better way why we need additional straps or additional clustering when a rocket when a rocket has to take off. Let us consider this example. Let us say I have a rocket whose initial mass is mi, and let us say it allows mass flow rate out of the nozzle at the rate m dot. Let us also assume that the rate at which the efflux leaves the nozzle is at velocity Vj. Let us put the units together, m dot so much kilograms per second, Vj so much meters per second. I want us to be able to calculate what is the initial acceleration of this rocket. How do I do it? You will recall in the last class we told ourselves that the force or the thrust with which a rocket is pushed up is equal to rate of change of momentum d by dt of mv, and here it is the momentum is Vj, therefore mvj, and therefore it is equal to m dot into Vj is the thrust over here. Now can you tell me what will be the initial acceleration of this rocket? Therefore the initial acceleration should be equal to the initial mass of the rocket into the acceleration a. That means force is equal to mass into acceleration, or rather the acceleration is equal to m dot into Vj divided by the value of the initial mass. And what did we tell ourselves in the last class? As I keep on adding more and more mass to the rocket, the initial mass increases and it becomes impossible for me to take it up. We will work out an example, a numerical example, to be able to figure out how we calculate the acceleration and how we decide what must be the level of acceleration. Because acceleration is also important. Suppose some human beings are sitting in a rocket, it cannot take off at very high acceleration, the man will go. Therefore there has to be some control on acceleration. Maybe we will have to address some things. Therefore acceleration we calculate like this, and therefore what did we now tell? Delta V is equal to summation of, I now use a simplified system and say I have Vj depending on the number of stages, and I have ln of the ratio of the initial to the final mass of the corresponding stages, that is I as I goes from first stage to the other, and this is how we calculate. If I were to take a simple example, I think we should in a theory class we should also try to simplify and get the terms together, and if I were to simplify things and write things as delta V is equal to Vj1 ln of 1 over the mass ratio 1, does it make sense to you? We said mass ratio of a rocket Rm is equal to the final mass divided by the initial mass, therefore it is Rm1 plus I have Vj2 ln of the second stage 1 over the mass ratio of the second, plus and so on. Supposing I have rockets in which the jet velocities are the same for all the stages, Vj1 is equal to Vj2 is equal to Vj3 and so on, and I have the mass ratios of each stage is also the same for all the rockets. Supposing if each stage has the same mass ratio and we say Rm1 is equal to Rm2 is equal to and so on, then what is it I get? I get delta V, and this I say is the mean jet velocity, and this I say is the mean mass ratio or the mass ratio are all the same, then I get the delta V is equal to n times the value of Vj ln of 1 over the mass ratio, right. That means by increasing the number of stages I am able to increase the delta V over here, but this is really not possible because the mass ratios of the individual stages may not be the same and the jet velocities of all the stages may also not be the same. You could relax these things by considering Vj to be different, you could consider Rm1 to be different, and I can keep on getting different ideal velocities. Maybe we will do a homework problem a little later and try to find out how to calculate the jet velocity taking into consideration a number of stages of rocket together. Well, this is all about the rocket equation and the number of stages, clustering of rockets, maybe putting straps in a rocket. We will look at some examples, but before looking at examples I thought, can we extend the rocket principle to what we have, see during Deepavali we fire crackers, something known as rocket is also there. What do? We have a launcher. Let us take a look. We have a bottle which is used as for launching rockets. We put that stabilizer which is the wooden piece of a rocket, and here you have this cracker which is filled with some black powder. We will look at its composition a little later, and you have a small squib over here and you light it and zoom goes this particular rocket, right. Actually a firecracker, right. Supposing I want to write the equation for this one, it should be the same equation, right. Therefore, here also I should say, well, the initial mass of the rocket will include the stick, the paper which binds it together, all this together, the mass of the gunpowder or let us say black powder which is available, that is the initial mass, and when the rocket is all consumed I am left with this wood, I am left with little bit of powder, or the powder is all burnt anyway, the paper which has still not got burnt, that will be my final mass. And therefore, what is the value of Vj? They have given a small hole here through which the gases are escaping, through that which escapes, and this is going to be my final value. But in cases like this, what happens is the value of the mass of powder we use is very small, and rather if I were to go back and write the equation what I wrote in the last class, namely delta V is equal to Vj ln of alpha plus beta plus gamma divided by alpha plus beta, wherein alpha was the payload mass fraction, structural mass fraction, propellant mass fraction, the amount of gunpowder or the amount of black powder which I keep this is very small compared to the weight of the stick and all this, and therefore gamma tends to be a small number. And in fact, it is not only in the Deepavali rocket that it is small, but if I were to look at another example, when I consider a rocket, I say we put stages, one stage after the other. I say let us say I have a 4-stage rocket. The initial mass of this rocket is going to be Mi, is going to be of first stage M1 plus the weight of the second stage M2 plus the weight of the third stage which is M3 plus the weight of the fourth stage which is M4. Now I have some propellant in the first stage, I have propellant in the second stage and all that, but whatever be the propellant I put here, in this first stage, since the mass of the total thing is so much, the mass of the propellant of the first stage divided by the initial mass of the rocket Mi is going to be small, because it carries so much mass that it is going to be small. The case is something similar to this, wherein the structural mass and the inert mass are and the payload mass, whatever, in a rocket nowadays you give good payload, what it carries is it gets some metal powder and once it reaches a height it releases the metal powder, and you see all these things going around. The mass of the payload plus the mass of the stick or the stabilizer plus the mass of the paper is going to be much higher than the amount of propellant in it. So, also in these cases which we say that the first stage, which we sometimes call as booster. What is a booster? It helps the it allows the rocket to take off, it boosts the rocket. Therefore, it is known as a booster stage, and a booster stage the mass of the propellant divided by the initial mass is a small number. If it is a small number, can we find out whether I can simplify the equation in some way? Well, is it going to be anything different from, let us say, the final stage, for which also we have derived the same rocket equation should hold good? Let us go back and see what happens in that case. Let us go back, write that equation again. Delta V is equal to Vj logarithm of, now I simplify it, please make sure it is all right, gamma divided by the structural mass payload mass fraction plus the structural mass fraction. This is the general rocket equation, it holds good for each of the stages. Now, I come back to the booster stage or to the case of a De Pauli rocket, right. For that I say the propellant mass fraction divided by alpha plus beta should be small, is small, because it carries so much of the mass above it, the mass of propellant is going to be small over here. Therefore, let us say this is equal to x, which is small. Therefore, now I get the equation delta V is equal to Vj ln of 1 plus x, where x is a small number. And what is ln of 1 plus x? X minus x squared by 2 plus x cubed by 3 but x is a small number, therefore, I can as well forget about square, cube and 4 and all that, and now I get the delta V for a rocket like a booster rocket or the bottle rocket which we used for De Pauli time is something like delta V is equal to Vj into, I plug back the value of the number gamma over alpha plus beta. Let us put it in terms of the dimensions. Therefore, I get Vj into mass of the propellant divided by mass of the useful part plus mass of the structure. Okay? We are just playing with numbers. And what is the mass of the propellant? Mass of the propellant is equal to the volume of the propellant into density of the propellant, and therefore, this becomes equal to density of the propellant into jet velocity into the volume over which the propellant occupies divided by mu plus ms over here. In other words, what is the comparison between the two? You find that in the other expression what we had for delta V, it was just Vj, let us write it out again, it was equal to Vj into ln of mi by mf, whereas in this case I get the figure of merit of the propellant as coming as density into this. Therefore, for a De Pauli cracker or for a booster stage, instead of Vj being a figure of merit, it becomes that the density into Vj becomes a figure of merit, and that is the distinction. In other words, the equation gets slightly simplified in that instead of meter per second Vj being a figure of merit, it becomes rho density of the propellant into Vj becoming a figure of merit, and of course, this becomes the volume proportional to the mass of the propellant and mu by ms. This is what we must keep in mind when we design the boosters. I will come back to this point when I show some slides, but this is something which is important, which comes very simply by looking at the expansion of this particular graph. All what I am trying to tell you is the following. Let us be very clear about our mission. The subject is simple and we must not feel diffident at any time. When I want to make a rocket, there are two important parameters I told you. One is Vj, it must be very high. The ratio of Mi by Mo must be large, Mf, right, must be large. But when we make a booster like this, or when I am making a firecracker, then in that case what is going to be different? Instead of Vj, I would like the density of the propellant into Vj to be large, and of course since this fellow carries so much mass, the density of the propellant also plays a role. And in fact, as we go along we will see, since the density of hydrogen is small, to be able to use cryogenic rockets which use hydrogen and oxygen as booster stages is not that advantageous, whereas if I use solid propellant which is a very dense material, maybe it is better for the booster stages. When we go subsequently, we will come back to this particular point. Well, this is all about rocket propulsion, rocket equation, staging and all that, but I think at this point in time let us go back and refresh ourselves on what we have learned through some slides, and then we will come back and see what we mean by propulsive efficiency, and then we will solve one or two problems. Let me come back to the slides. Here we see a two-stage rocket. Maybe the first stage gives you a velocity delta V1, the second stage gives you a velocity delta V2. The total velocity of this combination of the first and second stages delta V is equal to delta V1 plus delta V2. This is a two-stage rocket. Let us go to the next one. This is the first rocket which we designed in VSSC at Trivandrum. This was in the period maybe 70 to 78 we were working on it, and the first successful launch we had was in 1980. It was the simple rocket, it consists of 4 stages, and the first stage was solid propellant. I will give you a problem involving this rocket which we will do today. The second stage, this is the third stage, this is fourth stage. The total velocity which the rocket gives is delta V1 for the first one, delta V2 for the second one, delta V3 for the third one, delta V4 for this one, and maybe we will work out this problem a little later. All what I want to say is, well, we had a 4-stage vehicle. It is very deceptive, sometimes we feel we can keep on increasing the number of stages, maybe make infinity stages. I can go back, I can put any velocity what I want, but it is not correct. The more stages I have, the more commands I have to give to the rocket. I have to ignite the second stage, I have to separate it out, it becomes more complicated, and therefore the trend today is to go only for 2-stage to orbit or 3-stage to orbit, but people are still working on a single stage to orbit. Let's see what is the problem. We go to the next one. See, after the first stage, that SLV3 what I showed you here, it can only take a payload of something like 40 kg, it is very small. Therefore, it was necessary to go to higher payloads, and when I have higher payload, you cannot have the vehicle to accelerate because you need to increase the propellant weight. It was necessary to put 2 straps over here. Therefore, you had one strap here, I am sorry, let us go back, one strap here, the other strap here, the same as the first stage here, you had 2 straps, and then the second stage, third stage, fourth stage, and so on. This is known as ASLV. And now I show some more examples. These are the current rockets which fly. Ariane 5, by which we launched the INSAT satellites. It has been used to launch earlier, and even now we use them. You have 2 straps, first stage, then the second stage over here, Ariane 5. This is the space shuttle. It has been a workhorse for the US, and it has been decommissioned now. The last flight of space shuttle is over, and here also you have the space plane which comes back onto the ground, and this has something like 3 liquid engines all clustered together so that you get a high thrust, and you also have 2 straps, one strap here, the other strap over here. That means 2 straps for giving the initial acceleration. It starts off, and then you fire this this liquid engine in this, and it pushes itself up. The brown thing what you see is the hydrogen tank which stores hydrogen, which is required for this particular space plane over here. This shows, it is always nice to see the space shuttle taking off. These are the 2 boosters, solid rocket straps as I said, and you have 3 engines over here. Another workhorse of US is the Delta vehicle. Again you have a number of straps over here or cluster of engines. I will not get into the details of these things, but I wanted to show Soyuz, a Russian vehicle, wherein you have straps here or a cluster of engines here, and the main engine is flying, all the exhaust of this is interacting something like a ball, and the Soyuz was used for launching our first experimental satellite, namely Aryabhatta. This was in 75-76 period time frame. Well, again another part of US, another slide of Soyuz. Well, Atlas Centaur is something of Russian. Proton is another Russian launcher. All what I want to tell you is most of these vehicles have a number of rockets which are clustered and a number of stages. This is why I put some of these examples. Proton you have, we told ourselves launch a rocket can be launched from the sea, from the submarine it is taking off, and you see the water droplets splashing over here. Titan we leave. This is something about which I will give a problem which we will try to solve. This was the Saturn V, which was one of the very powerful launches which was used to take men to the moon, Apollo launch vehicle. And here again you have a number of stages. I think it is almost like a 5-stage vehicle, the ground having straps, then one after the other, and then you have the spaceship module over here which comes back. Maybe we will look when we are solving the problem. Again Soyuz. This is our PSLV, Polar Satellite Launch Vehicle of India again, and here again you find, yes, you have the first stage, you have straps, 6 straps or 4 straps could be put, then you have the second stage, third stage over here, and of course this is the GSLV. I think I will show the GSLV. Let us see if I can illustrate it. Yes, just watch closely. You first see the configuration. The configuration will consist of, as you see, it has 4 straps or cluster of 4 engines, 1, 2, 3, 4. There is a central engine. First the 4 straps fire, it generates thrust, the vehicle takes off, then the core also fires, and then you have a huge thrust, it keeps going, and once the 4 stages are there, it separates and falls down to the ground. Then the second stage fires, this is the interstage, then it keeps going further, then the third stage will fire, and it keeps going, the third stage fires, and it keeps going, and then after its task is over, it again gets separated, and then only the object or the spacecraft is there, and once it reaches the particular orbit, it sort of deploys, and this is how you get the final vehicle which goes into the orbit. Therefore, staging is a very important exercise in any of these rockets, staging, clustering, and yeah, this is the GSLV. As we just now saw, these were the 4 straps. This is the first stage, second stage, and the third stage. First these 4 stages are 4 straps are ignited, it gives you the thrust to take off. Immediately after takeoff, the core is also burning, therefore you have a huge thrust which it pushes itself, then the second stage fires, then the third stage fires, and then you had the separation as it were, and this is how a rocket functions. Well, we also talked in terms of a liquid rocket, wherein we said, or a water rocket, wherein you could have a water, I could pressurize it and push down. Maybe we will solve this problem in class a little later. Well, I think by now we should be therefore clear about what is the principle of a rocket, what is the rocket equation as it were, what will be the rocket equation modified for a booster, in which case rho Vj becomes more important than Vj itself, and then we talked in terms of staging, clustering or and also straps in a rocket. Is there any question so far? If it is so, maybe we should address yourselves. Now, this becomes the essence of what we are going to do. If this is clear, let us go to the next part of the subject. We will ask ourselves, are there certain things like efficiencies? We people are people who are used to analysis so much that anything what we want to do, we will say, hey, what is the efficiency of a rocket? How do you say efficiency? We are looking at the rocket flying up, therefore I want to find out, well, we say rocket propulsion, therefore I say what is propulsive efficiency? How do I define it? It has to do something about the forces, how it is moving up, or the power which you are giving, the power it is producing. Therefore, I say, well, propulsive efficiency is something like the power generated by a rocket, or let us say work done by the rocket per unit time, let us say, divided by what should it be? What is your guess? Work you do on the rocket to make it go up, and what should it be? The work done by the rocket, again let us say work done by rocket per unit time plus the work wasted by the rocket. That is the total work which you are doing on the rocket per unit time. How do I put these things down mathematically and tell you what is going to be the propulsive efficiency? Any guesses? Anything? You all should be able to tell me something more. Yes, I'll give you an idea. The work done by the rocket is equal to force into distance, right? The force of a rocket, we told ourselves, is equal to m dot Vj into distance, let us say L. Therefore, I say work done by the rocket per unit time is equal to m dot Vj into the velocity of the rocket, L over T, and therefore, we say so much joules per second or so much watts. Is it all right? Useful work, that is the useful work. Let us try to sketch this out. All what we are telling is, maybe I have a rocket going up, it goes with a velocity v, it is pushed up with a pressure force. Therefore, the useful work which is done by the rocket is the force into the velocity per unit time. Now, does it waste anything? What is the waste? How do I get the waste from it? Anything getting wasted? See, as the rocket is getting pushed up, the plume is going down. Again, I picture myself, I am in the inertial frame of reference, I am standing here watching the fun of the rocket going up. What do I see? I see that this plume is now going down with a velocity Vj respect to the rocket, or rather, if as the rocket is going up, the plume is going up with a velocity v minus Vj. I will give you an example, see on some of these, you go out of your hostel and maybe early morning 5:36 and watch maybe the some of these jets flying across Chennai. You will see the trail, maybe an aircraft is moving, let us try to picture it out, let us picture the trail. aircraft is moving, you see the aircraft going, and then you will find the smoke from this trail is also following this at a slower speed, right. Why does it have to happen? Maybe because this fellow is leaving the rocket with a velocity Vj, rocket is moving with a velocity this, therefore you see this particular jet or plume as it were following it up with a velocity v minus Vj. Therefore, what is being wasted? The energy content of this is getting wasted because it is getting lost. And what do I see? I, in the inertial frame of reference, look at the work done by the rocket per unit time, but I also see that this is getting wasted, and what is my waste? That kinetic energy is getting wasted, half mass of this into v minus Vj square, or what is the rate at which I am seeing is half m dot into v minus Vj square, that is a waste. That means rocket is going up, this fellow is still following it up like this, and therefore this is a waste, it could have done much more job had it not got wasted, and therefore how will I put my propulsive efficiency together? I will now write the equation as eta p propulsive efficiency is equal to the useful work done, which is equal to m dot, Vj is the force into v of the rocket, divided by useful one m dot Vj v plus the kinetic energy per unit time m dot into v minus Vj whole square. Please let us be very clear. See, this will keep on haunting us, we will have to define the efficiency of a scramjet, we will have to define the propulsive efficiency of an aeroplane. We will find that there are some optimums, and I find some research work going on. I will refer you to a paper in today's class itself. The way people tend to think, can we improve the rocket by looking at these efficiencies is the question. Well, let us simplify this equation. This is equal to m dot into Vj into V divided by, now if I were to look at this, I bring 2 on top, right, then I get 2m dot into Vj into V plus m dot V square plus m dot Vj square minus 2 into m dot V into Vj. Is it all right? V square minus 2 V Vj plus Vj square, V square, Vj square, 2 V Vj. You find that this and this gets cancelled, m dot gets cancelled on the numerator and denominator, and what is the propulsive efficiency? Therefore, equal to, propulsive efficiency is therefore equal to 2 of V Vj by V square plus Vj square. Is it all right? V square plus Vj square in the denominator. Let us simplify it, let us divide by Vj the numerator and denominator, or we get V divided by Vj square 2 V by Vj divided by 1 plus V by Vj whole square is equal to efficiency of propulsion. Is it all right? Now, I want to ask you, when will the propulsive efficiency be a maximum? Just look at this expression, just be unbiased and tell you whether I can identify a condition for the propulsive efficiency to be a maximum. We will anyway solve, we will find out the maxima and solve it, but by looking at this expression, can you tell me when should the efficiency be a maximum? Yes? anybody by looking at the expression? All what we are saying is NP square is equal to 1 plus or 2x divided by 1 plus x square. What should be the value of x for which eta p is a maximum? Efficiency cannot be greater than 1, it has to be 1, and we find that the moment v by vj is 1, it becomes 2 by 1 plus 1 2. Therefore, by inspection itself I can say when v by vj is equal to 1, then the propulsive efficiency will be a maximum of 1. And how do we do it? Normally we go through the mathematics of it. We will tell ourselves, let me differentiate it. Let's do that exercise. D eta p by d of v by vj must be equal to 0 to give me the maxima, and for that you would say yes, denominator square into denominator 1 plus v by vj square into differential of numerator 2, right, minus what, numerator into differential of denominator 2 of v by vj, and this must be equal to 0. Therefore, I am not really bothered, I do not want to write 1 plus v by vj whole square over here, and therefore, what does it give me? It gives me 2 into 1 plus v by vj whole square minus 4 into v by vj square is equal to 0. What does this give you? 1 plus 2, 1 minus 2 v by vj, 2 minus 2 into v by vj, or rather it gives you that v by vj must be equal to 1 to get the maximum this particular value. Could you do this? See, but we must be able to draw inferences by looking at this, and by inspection itself what we get is what comes out of differentiating over there. Therefore, all what we are trying to say is, well, if I were to plot the propulsive efficiency of a rocket eta p as a function of its flying velocity divided by the jet velocity, the efficiency becomes a maximum when the velocity is 1 and thereafter it begins to go down. Therefore, this gives me some suggestion that if I can have the exhaust velocity equal to the velocity of flight, then I may be able to get the maximum propulsive efficiency, or rather as the velocity of the rocket changes, if I can somehow keep on changing my exhaust jet velocity, I can get a better efficiency. But then it is just not possible. A rocket is a thing which is rapidly accelerating and all that, it is very difficult to meet this, but there are some references and one paper which deals with this and which is very exciting to read this. I will give you that reference, maybe you all should take a look at it. It is by King, Junior, MK. The title of the paper is Rocket Propulsion Strategy based on kinetic energy management. It appeared in Journal of Propulsion and Power. I just write it down here, Journal Propulsion and Power of AIA. the volume number is 14, it is in the year 1998 and the page number is 270 to 273. Maybe if you all should go and take a look at it. See, we know it is not possible, but still what does he try to do? Can you somehow get something to do with Vj and try to see whether you can get a better propulsive efficiency. Such ideas are useful, because later on we will get into electrical propulsion, nuclear propulsion. We will try to see whether we can somehow make the rocket more efficient, because as of today, even to go to Jupiter, we saw it takes something like 5 years. If you have to go to the Kuiper belt, it takes something like 10 years. Where are we with respect to going to different galaxies, different stars? We need to improve the rocket. Therefore, these give some clue of this. Therefore, this article by King is something which was thought provoking. At the beginning itself, he says it is a blue eye tutorial for students, but I think it is something about which we should take a look. But having said that, I want to ask you one question. Under what conditions is propulsive efficiency a maximum? See, we told ourselves a rocket is flying up, and now when it is flying up, you see the trail following it. What is the condition of the trail or the plume when V by Vj is 1? That means the kinetic energy of the plume is what? 0. Well, what happens to the trail? I see a rocket going up, the plume is also going up. What will happen to the plume when propulsive efficiency is 1 or maximum? That means V minus Vj is 0. That means it will be dead static. That means it has no energy at all. In other words, all what we are saying is the value of this plume, it becomes V is equal to 0. It does not follow the rocket, it just stays put at a particular place. And in other words, we have made use of the total kinetic energy for pushing the rocket up. Now, this is the inference of the propulsive efficiency. I do not think there is anything else to do. I think I will go through 2 or 3 case studies. I will start with the SLV3 problem, or the how we calculate the masses, payloads and all that in the first part, and then do a simple problem using water rocket. But since this water rocket is here on this particular slide, maybe I will get started with this. Let us try to solve this problem. See, the problem which I will pose to you is the following. Maybe I will put it up on the board just now. See, you have a bottle which contains water, you have high pressure gases above it. I want to push out I push the liquid water or the water out through this using compressed air. The compressed air pressure is told to be something like 0.35 MPa, that is 3.5 atmospheres. I want to find out the size of the hole such that the rocket leaves the ground at a given acceleration. This is all what I want to do. How do I size this rocket? This volume is given, this volume is given, but I need to know the size of the vent or the hole such that the rocket can leave with a given acceleration. Let us do this problem. Therefore, let me write this problem on the board. The mass of water is given to be 0.5 kg. You have in a bottle 0.5 kg of water. The air is relatively massless, which is above, and the pressure of air is 3.5 into 100 kilopascal, that is 0.35 MPa. You know, it is also told that the mass of the bottle, that is the structure of this, all these things put together, is again, that is the mass of the structure is 0.5 kg, and all what we are interested to know is, we would like the rocket to leave with an acceleration, the level of acceleration is to be 0.5 g, that is g is the Earth's acceleration due to gravity, or we say gravitational acceleration is 9.81 meter per second square. With respect to that, it is half the value of the gravitational field, that is the value with which it must get pushed up. Now the question asked is, what must be the size of the diameter of the vent or the hole by which the water flows out? How should we be doing this problem? See, everything is available to you. You have a mass of water 0.5 kg, let us say the mass of the water is mass of propellant which is used for pushing it up, 0.5, the mass of the structure is equal to 0.5 kg. What is told to you, what is not, I have not told is, there is no payload in this, just the bottle is moving up. Therefore, the useful payload mu is equal to 0 kg. Now you are asked to find out what must be the rate at which water is getting pushed out, because if you know the rate at which water is getting pushed out, I can find out what must be the diameter of this particular hole. Therefore, how should I do this problem? What are the things I should do? Let us say I first want to find out what is the velocity with which the water will leave this particular hole. In other words, I am interested in finding out the jet velocity Vj. Yeah. How do I get Vj? We said Vj, I must find out. How do I get the value? The gas pressure is 3.5, the ambient pressure is 100 kilopascal, that is the air pressure, Pa is equal to 100 kilopascal. Water is incompressible. How will I find out? Let us neglect the height of water. Maybe from Bernoulli's equation we can say P for the compressed air, which is over here, or compressed gas, let us say P by rho plus what? How will I write the equation? How do I calculate the value of Vj is a question. I am pushing out with pressure over here. What is the flow rate, or what is the velocity with which water will move? Let us say you have on this surface of water, the pressure is 3.5 into 100 kilopascal. On the surface of this, the pressure is 100, because this is how it is seeing the ambient. Therefore, for the water column I am writing the Bernoulli equation. Therefore, I have pressure on top, which is equal to 3.5 into 10 to the power 3 plus 2 5 in 3.5 yes into 100 into 1000 Pascal divided by the density of water, plus this is being large diameter, the velocity is 0, therefore velocity squared by 2 is equal to 0, is equal to the one which is at the bottom 100 Pascal divided by the density of water plus the velocity with which it is exhausted out divided by 2. Is it all right? or rather we could have just told ourselves, well, Vj square is equal to under root of 2 of delta p divided by rho. No, we are talking in terms of V square is equal to delta p, yes, divided by rho, and that would have given us the same thing what we are solving for, namely is equal to under root 2 into 3.5 minus 1 is it 2.5 into 10 to the power 5 divided by density of water 1000 kilogram per meter cube. Is it all right? Then what is the value coming out to be? If you calculate, you will get it to be equal to 22.36 meters per second. We should be able to do any problem, and that is why I chose this particular water problem. You are pushing out water, you are pushing out with some pressure, you know the velocity with which it is coming out, and that velocity with which it is coming out is 22.36 meters per second. What about the? See, I said let us neglect the height because the height is small, because you have the pressure which is so high that the height will really not matter. But in a real problem, yes, I would like the height of water to be the weight of water due to the height also to be considered, yes. Now, we just wrote the Bernoulli equation and tried to do it. Okay, now I want to make use of this jet velocity and find out what must be the diameter of this. But what is given to me? Something important is given to me. It is told that the rocket should leave with an acceleration of 0.5 g, or rather with an acceleration of 4.905 meter per second square. How do I get this? Somehow I have to get this. That means I must be able to calculate the force, and that force I have to convert it to acceleration and make sure I get this acceleration. How do I do this problem? Let's revise what we have just now done, and in the process do this problem. I would like to find out what is the force which is generated by the particular rocket divided by the initial mass of the rocket, which is the acceleration of the rocket, and the rocket is going up. Therefore, what is the acceleration with which it is going up? It is equal to F minus the gravitational acceleration of the mass divided by mi is the true acceleration with which it is going up. See, this differentiation is important. I say force is what is pushing it up. As it is pushing it up, it is the acceleration, the gravitational field is also exerting a force equal to mig. Therefore, F minus mig divided by mi must be A and not this. This is what is with when I have no gravitational field. Therefore, now how do I solve this? This A is given to me as 0.5 g. Let me erase this portion by just writing the Vj is equal to 22.36 meter per second, yes. What is the value of F? Let us assume let water flow at the rate of m dot kg per second, because if I know the water flow rate, I can calculate this diameter. Therefore, F is equal to m dot kg per second into what? How do you calculate the force? We have done it. Change of momentum, mvj is momentum, force is equal to d by dt of mvj, which is equal to m dot vj. Therefore, what is missing here? What should I write here? Vj, m dot Vj is force, so much meters per second. That means the thrust is equal to m dot Vj, and Vj we have already calculated is equal to 22.36 into m dot is equal to the force. Now what is the force? I go back to the equation what I wrote here, I get F minus mi into g divided by mi is equal to 0.5 g. Here g is 9.81. What is the value of the initial mass of the rocket? 0.5 plus the structural mass is 0.5, which is 1. Therefore, I know the value of mi, I know the value of g, I can calculate the value of f. Let us calculate it out. Therefore, f is equal to I take it on this side, we said mi is equal to 0.5 plus 0.51, it becomes 1.5 g, that is 9.81, okay, and mi was 1, therefore force is equal to 1.5 into 9.81 into, is there anything else missing? What is the value of mi we have got? See, we said mi is equal to totally 0.5 plus 0.5, right, and therefore I can calculate the value of f, and once I calculate the value of f, which is 1.5 into 9.81, I put it over here, and what I get is the value of m dot and if I know m dot, how do I calculate the throat diameter or the diameter of the vent, as it were, the diameter of the hole? M dot is equal to, we get the value, the density of water into the velocity of water into the area, area is equal to pi by 4 into the whole square. You have already calculated the mass flow rate, density of water is 1000 kg per meter cube. You have calculated the Vj, this is the velocity with which the liquid is leaving, Vj square, pi by 4, therefore the only unknown is dV, and this is how you design the vent diameter. I think I will leave it as a carry over homework for you all. All what I want to tell you is, it is possible to calculate the thrust, you need the value of Vj, Vj we find through simple calculation it is possible, and once you know this, I can always relate it to the acceleration. I will not complete it, I will just be spending too much time on it, I rather go to the next problem and do it. But can we all, can we compare the notes on, let us say in the next class, just let us share what is the number of the diameter what we get. Let us say, is it going to be a few mm, is it going to be a centimeters, is it going to be meters, maybe I would like to take a look. By intuition you expect it to be about a centimeter or 2, right. Let us do it. I think with this maybe I think I will stop the class. I wanted to do a problem on the masses, structural masses, structural mass, maybe the propellant mass and the acceleration for some multi-stage rocket vehicle. Maybe in the next class I will just go through 1 or 2 small examples on it, and then we go to the next topic, which is on nozzles, that also we will cover in the next class. Well, thank you then.